So now we're going to talk about a little bit more on linear block codes, introduce notation having to do with parity check matrices and generator matrices, how you describe the codes. We're not yet going to talk about how we design good codes, just how we describe the codes, and then how we would go about decoding simple linear block codes. So you can define any nk linear block code by a k by n generator matrix. Now, again, a linear block code is basically it's a subspace of a vector space. And the linearity property is very important for implementation. So almost all codes used in practice are linear. And they have two advantages. They're nice for analysis, which means research people like to assume linear codes, but they're also, the nonlinear codes have almost no advantage in theory over linear codes anyway, and linear codes have, in addition to being easier to analyze, they're easier to implement, a lot easier to implement. So for those reasons, the focus in coding is almost entirely on linear codes. So we use a generator matrix, and the codes, the set of code words, remember we're going to need 2 to the k code words. They're all possible 2 to the k linear combinations of the rows of this generator matrix. Now this is a binary matrix if we're talking about binary codes. So it has k rows and n columns. And notice that linear combinations of the rows here would give us a code word of length n. So we're talking about nk codes. So if our information sequence is this k-bit sequence U, then the corresponding code word, we multiply the first bit in the information sequence by the first row of G and the next bit by the next row of G, etc. Addition is always modulo 2 here. I should have mentioned that when I showed that little diagram of a convolutional encoder, and we had those 2 little adders there. So the addition is modulo 2. It's not real addition. It's, if you want to think in terms of logical functions, it's an exclusive OR operation. 1 plus 1 is equal to 0. And 0 plus 1 is equal to 1. So it's all modulo 2 arithmetic here. And if we're not going to discuss non-binary codes, I don't think, but I will mention a little bit in the LDPC code part about non-binary codes. Those are also always defined over fields with more than 2 elements. So they still, with the code words and everything, would satisfy the algebraic properties of a field. Okay, so the sum of any 2 code words in a linear code is also a code word. That's just the property that's a subspace of a linear space, of a vector space. So if V1 and V2 are both code words, then V1 plus V2 is also a code word. And the all 0 vector is automatically a code word in every linear code, which we can see easily. If the input sequence is all zeros, then we multiply every row of G by 0 and we get the all 0 code word. So nonlinear codes maybe don't have the all 0 code word as a code word. So I said this before, it's a k-dimensional subspace of the vector space of all binary n tuples. These are sometimes called group codes. For those of you that are algebraists, it's a group. The set of code words forms a group of dimension k. So a little example. This is the same example we had earlier, I think. K equal 3, so we have 2 to the k or 8 different messages. These are the 8 possible 3-bit sequences. And here is a code, which we could where we assign the code. It's a linear code also. So this can be described by a generator matrix, and we'll see what that might look like. So the first thing we do is we can write out the equation. So we're kind of working backward here from the list of code words back to the generator matrix. we can look at the equations here. V0, the first bit here, is always given by the sum of the U1 and U2. Okay, you can see that 2 zeros here give us 0. 1 plus 0, 1 plus 0, 0 plus 1, 1 plus 1, it gives us these 1s. 1 plus 1, 1 plus 1 gives us 0. So the V0 bit is always the sum of U1 plus U2. In a similar way, V1, the second bit here, is U0 plus U2. So here we see 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, etc. So, and V3, or excuse me, V2, is U0 plus U1. It's the sum of the first two bits. And we can see these two rows give us 1 here, 1 plus 1 is 0, etc. So these are the rules by which the first 3 bits here were formed. And if you look at the last 3 bits here, you'll see that they're actually exactly equal to the 3 message bits. So the equations for the last 3 bits are V3 is U0, V4 is U1, and V5 is U2. So if we have a linear code and we write out this table like this with the messages and the corresponding code words, that defines the linear encoding equations. And then we can from these then we can determine what the generator matrix is. Otherwise, V0, it says we're going to multiply. We know V0 is U1 plus U2. Okay, so that means that we get V0 by multiplying this input information sequence by the first column of this matrix. That means the first column should have a 0 here and 1 here and 1 here. Because U0 is not involved in this equation, but U1 and U2 are. And the second column should have a 1 in this position and a 1 in this position, because we're U0 plus U2. Okay. And the third column should have a 1 in the first 2 positions, because we're U1 plus U2. 2 1s here, but no 1 here. And the last 3 columns should form an identity matrix. Okay, because these 3 bits are identically equal to these 3 bits. So that gives us this generator matrix. Now I said kind of we worked backwards. I started from the list of code words and worked backwards to get the generator matrix. You can define a code from the generator matrix and then go the other way. And for each of the possible 3-bit sequences, you can write down the code word, and you could work otherwise starting with this matrix, and say you take the message 101, that's going to say we add the first and the third rows, whoops, which means we're going to get 101, 101. So if we go back to our table, here, the message 101 gives us the code word 101, 101. So you can look at this either way. You usually start by defining the generator matrix, and then that defines the code words. But if you want to look starting at the code words and work backwards, you can find the generator matrix like this. Any question there? Now, it's common for linear block codes to be put in systematic form. They don't have to be. It doesn't give you any better error protection performance or anything, but systematic form simply means that, just like the one we had, that the message bits appear directly as part of the code word. So otherwise, if you just looked at a certain k bits in the code word, those are the message bits. So that implies that there's an identity matrix in the generator matrix. So this is any code in systematic form will have a generator matrix that looks like this. Actually, this identity matrix could be any k columns. Okay, it's convenient to put it over here on the right. And then the other part of the matrix is what's called the parity check part of the matrix. And that's why we use the symbol P here. In general, we use symbols G to represent the bits in a generator matrix. But when we make it in systematic form, we take the parity. This is always, the information part is always, or message part is always an identity matrix. The parity part, we use P's to represent those. So we have K unaltered message bits and then an additional N minus K parity check bits. These are the redundant bits that we talked about adding back in the first lecture. And the encoding equations for the parity bits then are given by this expression, and you can see this again if you multiply U, the input sequence U0 through UK minus 1 times the first column here gives us exactly, whoops, the first parity sequence here for J equals 0. And then if we multiply U by the second column, we get the second parity check equation corresponding to J equal 1, etc. And the message bits are just the message part of the code word is just given here for the K message bits are equal to the last K bits in the code word. Sometimes people like to put the identity matrix in the first K positions and the parity matrix in the last K positions, but it doesn't matter either way you can do it. Like I say, they can be in any K positions, the identity part. So each parity bit then turns out to be, these are formed as a modulo 2 sum of certain message bits. Okay, and that's basically where you get your redundant bits. You have your message bits, and those are part of the code word, and then you form N minus K parity bits as linear combinations or modulo 2 sum of certain message bits. And certain means, there's good ways of doing this and there's bad ways of doing this. So there's good generator matrices and there are bad generator matrices, and you'll hear more about this afternoon. Now, there's another way of describing linear block codes, which is important when we talk about low-density parity check codes in particular. The primary way linear block codes are described is through the generator matrix. That was the standard classical way of defining linear block codes. It was always known that you could define them using a parity check matrix, but when we talk about and the advantage in terms of defining codes in terms of their generator matrix, it's easy to see how to do the encoding. Okay, the encoding is straightforward. The parity bits are just formed by certain linear combinations, which are given directly by the bits in the parity part of the generator matrix. So the generator matrix point of view of defining a code is oriented towards making it easy to encode. The parity check matrix view of defining a code is more towards making it easier to decode. Okay, because checking parity is what you have to do to decode. So that's done from the parity check matrix. We'll see this in a minute. So, and low density parity check codes, for example, are defined from the parity check matrix. And one of the issues is, once you define these codes, well, what are the corresponding generator matrices? Okay, now if the code is small, if it's got a small n and k, it's not a problem to find the generator matrix. But if you have large codes, it can be difficult to find a generator matrix if you only define the code in terms of parity check matrix. We'll say a little bit more about this when we get to low density codes. So the way of defining a code from the parity check matrix is a binary n tuple, and remember there's only a subset of 2 to the k binary n tuples that are code words out of the 2 to the n possibilities. So a binary n tuple is a code word if and only if this relationship is satisfied, where H is a so-called parity check matrix, and here we take the transpose of it. So for example, we could consider this. Here's a 7-4 code. We've been working with a 6-3. This is a 7-4 in systematic form. And this is from the generator matrix. Now we can write out the encoding equations just as we've learned how to do this. V0 is the information bits times the first column here, which is U0. Actually, there's a typo here. Did you know that? This should be U2. Yeah. I think that's the only place. I don't think it survived. But so this is U0 plus U2 plus U3. This V1 is U0 plus U1 plus U2. V2 is U1 plus U2 plus U3, and these are just the systematic part. So now, to kind of view this from the parity check point of matrix point of view, we can rewrite these three equations. There's 3 parity bits here and 4 information bits in the 7-4 code. We can rewrite these 3 equations by taking these U's and substituting in these values of V. So each U0 we replace by V3, each U1, not this one because it's not there, by V4, and the U2s by V5, and the U3 by V6. And that's going to give us these 3 equations. And if we can also pull then everything over to the left-hand side. And again, modulo 2, you just add the bits to the right-hand side, to both sides, and you get 0 on one side and all the bits on the other side. So you get these equations. And these can be viewed in matrix form. You could write this in matrix form as you have a 7-bit code word here times this matrix, which the first column represents V0 plus V3 plus V5 plus V6 equals 0. That's this equation. The second column is V1 plus V3 plus V4 plus V5. Whoops. Yeah. That's equal to 0. And the third equation is V2 plus V4 plus V5 plus V6. That represents this equation, which is equal to 0. So this is a matrix representation of this. And we can, this would be what we would call H transpose. And the corresponding H would be just this thing with rows and columns interchanged, which would be of this form. You'll notice that the top 3 rows here are an identity matrix. So when we go to the, not the transpose version, we get a 3 by, in that example, a 3 by 3 in general, an n minus k by n minus k identity matrix here. And then the rest of that matrix, this, if you look back to the generator matrix, and these aren't on the same picture here, so you have to use your memory a little bit. But the like the first row is 1, 1, 0, and the second row is 0, 1, 1. That's the first 2 rows of the generator matrix, and the other 2 are the same also. So this lower part of this H transpose matrix is actually the left part of this generator matrix. This is all when the matrices are in systematic form. The code is in systematic form. So then when you transpose this, it becomes the right half of H, and you just get the P's here, just like we had them. We go back to the general, yeah, just like we had them here in the generator matrix. So when you have a code in systematic form, it's easy to convert from the generator matrix to the parity check matrix. You simply, in the parity check matrix, in the generator matrix, you have a k by k identity on the right. In the parity check matrix, you have an n minus k by n minus k identity matrix on the left. In a generator matrix, you have a P parity matrix, K by n minus K on the left. And in a parity check matrix, you have an n minus K by K matrix on the right, P transpose, same matrix. So you can flip back and forth easily between the generator matrix and the parity check matrix if the code is in systematic form. For example, here's our example again. So we had this is the P matrix in G, and the transpose of this now is here in H. And this is the identity part of G. It's a 4 by 4. Here we have the identity part of H, which is 3 by 3. So actually, it's very straightforward if you have a code in systematic form to flip back and forth between the parity check matrix and the generator matrix. So if you define a code in terms of the parity check matrix in systematic form, and you want to know what the generator matrix is so you know how to encode it, it's easy. So I said earlier with low density parity check codes, this can sometimes be a problem. Why is it a problem? Well, because low density parity check matrices are not defined in systematic form. Actually, systematic form would be a bad code. A parity check matrix which had a systematic part would perform poorly. So low density parity check codes typically are non-systematic. So then these are powerful codes. They're big. They may be in standards even. They can run up to 10,000 bits. So you think of a matrix, a binary matrix, 5,000 by 10,000, and it's not in systematic form. How do you find the G corresponding to that to do the encoding? Okay, you have to convert it to systematic form. Okay, there are ways of doing this, but it becomes very difficult for large values of the parameters. So this is an issue with low density parity check codes, which we'll say a little bit about later on. Okay, any question on this?
When generator matrix and parity check matrices are written in form of systematic, they are written in systematic form. So I think they should be unique, is it?
Yeah, when they're written in systematic form, right? It's unique, right? Yeah, it's a good point because you can have many generator. Okay, in fact, maybe this didn't make it onto the. Somehow, in order to boil the lectures down to try to get all our fundamentals in, I guess, 10 classes we've got. So there are some things that didn't make it in. So in general, and I think you can see this, since VH transpose must be 0 for any code word V, then in general, GH transpose must be equal to 0. The generator matrix G times the transpose of H must be equal to 0. Because anything in the row space of G is a code word, and we know that any code word times H transpose is equal to 0. So that's a general relationship that must be satisfied as GH transpose is equal to 0. But if you specify an H, there may be many G's which would result in GH transpose equal to 0. Or vice versa. If you specify as a G, there may be many H's which would satisfy that relationship. So you can just think in G, you just switch the rows around or something and do any operation that doesn't change the row space. You get lots of different G's which would still give you 0 when multiplied by H transpose for a particular H. So that, again, going back to the comment on low-density parity check codes, you can have a non-systematic H matrix, and you can use a systematic encoding if you can find it. If you find any generator matrix, then you could, by row operations without changing the row space, you can convert it to systematic form and have a systematic encoding. So even though the low-density parity check code may be defined in terms of a non-systematic H matrix, you can, in principle, find a systematic G matrix for it and encode that way. In general, it's a little easier to encode. I mean, the encoding is just U times G. But if part of the generator matrix is an identity, if it's systematic, that makes it a little easier. You only have to multiply U times the P part. The other part you already know. So these are just some little issues. I'm getting ahead of myself a little bit talking about the low density codes. So I said that one of the advantage of the kind of defining codes from the H matrix point of view, it's more related to decoding, whereas the G matrix is more related to encoding. So let's say we've got V, it's a code word, in a code which has generator matrix G and parity check matrix H. Now we're going to assume that it's transmitted over a binary symmetric channel, and we get a receive sequence R, which is V plus E. E is an error vector, or an error pattern, which is just a binary vector which represents every position in E, which is 1, represents a position where R and V do not agree. And the positions in E that are 0 are positions for which R and V do agree. So you transmit a code word V, every possible received sequence R is going to imply some error pattern E that caused R to differ from V, or to be the same as V, which would be our desired outcome. So the 1s in E represent the transmission errors, okay, as I mentioned. So now the decoder unfortunately doesn't see E. It'd be easy if it did, right? You're trying to estimate where the errors are. Well, if you could see E, you'd know where they are and you could just go correct them, okay? But all the decoder does is it sees R, okay? And it's got to determine then, first of all, it's got to determine if there are errors in R or if not. And if there are, it's got to find out where they are and correct them. Now, from the definition of the parity check matrix, it's direct that we know that if and only if a vector is a code word, it's going to give VH transpose equal to 0. So the first thing to do when you receive R should be to multiply it by H transpose. If you get 0, then you know R is a code word and you're done. You're not detecting any errors. If it's not equal to 0, then you know there must be errors, because any code word, if what you got was the transmitted code word, it would have to give 0. So you compute this syndrome. It's an n minus k tuple. You multiply R, which is an n tuple, by H transpose, which is n by n minus k, and you get an n minus k bit vector called a syndrome. Binary. It's all binary. And R is a code word if and only if this is equal to 0. If the syndrome's not 0, R is not a code word, and we know that errors have been made. So we've done the error detection part of the decoding problem just by computing the syndrome. If the syndrome is 0, we know R is a code word. We haven't detected any errors. Doesn't necessarily mean that no errors were occurred. We could have had the situation where the error pattern just by chance changed one code word to another code word. And then that would still give you a 0 syndrome. Now, in a linear code, this can only happen when the error pattern itself is a code word. So if the error pattern is a code word, and you take your transmitted code word, add to that the error pattern, which is a code word, you get another code word, because it's a linear code. And that's still going to give you a 0 syndrome. So there's no way to detect that. And that's why Audrey will talk this afternoon about minimum distance and things like this. That's why you want a code. You don't want a small number of errors to be able to change one code word into another code word. If you had two code words which differed in only one position, then just one error could change one code word into another code word. There'd be no way of detecting it. So you want kind of the minimum Hamming distance between any two code words to be as large as possible in order to avoid this problem. So that's something, that's a design. So this starts to give us an idea of, okay, how do we design these G matrices? Well, we want to design them so that the minimum Hamming distance between any two code words is as large as possible. So the syndrome, this is something we can observe since the received sequence is the transmitted code word plus the error pattern. We can write this product as the sum of these two terms, and we know this guy is equal to 0. So actually, the syndrome really depends only on the error pattern. It doesn't depend on which code word was transmitted. It just depends on the error pattern. So if we go look at this example, this that we've been working with, this is the H matrix. Say we receive this. I can't remember if this is one of the code words or not, but we could look at it. We multiply it by the transpose of this, which is just this thing transposed. And what it's saying is we're going to add row 2 and row 7, this row and this row, and we get 1, 1, 1. So the syndrome is non-zero, which means that this cannot be a code word. So we've detected errors, and we need to now try to go about the job of error correction. He said, in general, we get the error pattern is an n-bit vector, and H is given by this form. So these syndrome equations, like for example, for J equals 0, we get E. So it's actually E times H transpose that we're computing. So we're really taking the inner product of E with the first row of H here to get S0. And so we get E0, or in general, E sub j for any one of the rows here. And then we get the error positions from position n minus k to n minus k, n minus k up to n minus 1 multiplied by these parity bits here in the parity check matrix. So this is just in general what these syndrome equations look like. Okay, so there's n minus k equations here. This is in general when we compute a syndrome, we have n minus k equations. And we've got their linear equations. And we've got but n unknowns because the error pattern is of length n. So we've got more equations than unknowns, so we can't get a unique solution. So the idea is, in principle, we would like to solve for the estimated error pattern, but we don't have enough equations. I mean, what if we had enough equations? What if we had n parity checks? Well, the length of the code word is n. If everything was a parity check, we wouldn't have room for any information bits. So we'd be transmitting at rate 0. So obviously that doesn't make sense. So you're never going to be able to solve uniquely for the error pattern here. But what do we want? Of course, we want to find the most likely error pattern, the one that minimizes the probability that we're going to decode incorrectly, that we're going to make a decoding error. So since there are k more unknowns than there are equations, and everything is binary, there's 2 to the k possible solutions. But only one is the real error pattern. Okay. The others are not. Now what we want to do, again, to minimize the probability of decoding error, we want to pick the most probable error pattern that satisfies the above equation. Okay. Now I think from the previous discussion on a binary symmetric channel, we had said that the maximum likelihood decoder chooses V hat as the code word which was closest to the received sequence in terms of Hamming distance. Or if so, we would want to pick V hat as the code word which has the minimum Hamming distance to the received vector. Okay. Now, the Hamming distance between V hat and R is just the number of non-zero positions in E, right? That's the number of ones in E, which changes bits in R, makes them different in V hat. So minimizing the Hamming distance between R and V hat is equivalent to minimizing what we call the Hamming weight. I guess we didn't write out this definition of E, of the error vector. So of all the possible solutions, we want to pick the one which has the lowest weight, the lowest number of ones. I mean, the Hamming weight of a binary vector is just the number of ones. So picking out of the 2 to the k possible error patterns which could cause this particular syndrome, okay, we want to select as the most likely, the one that's going to minimize the error probability to be the one with the lowest weight or the fewest number of ones. I mean, that makes sense if you think about it from what we said earlier, that a channel error is less likely than a correct transmission. Epsilon is smaller than 1 minus epsilon. So it's always, among a set of error patterns, the one with a smaller weight is always more likely than one with a higher weight. Okay, because fewer errors are more likely than more errors. So that corresponds to minimizing the Hamming weight of the error pattern. But here we're not looking at all error patterns. We're just looking at those which are possible solutions to this particular syndrome that we've calculated from our received vector. So we can look again at this example. Here's our H. Let's suppose that this is transmitted, which is the code word corresponding to the top row. Oh, wait a minute. This is the H. This is not G. So let's just say this. Just to verify that this is a code word, this is saying that positions 1, 4, 6, and 7 should add to 0. So this column plus this column, that gives us 0, 1, 0. And the sum of these two columns also give us 0, 1, 0. And you add those two together, you get all zeros. So you can see that this is a code word, just so you're sure this is a code word, and we didn't put something in here which is incorrect. So say this is transmitted, and let's say this is received. So the same thing is transmitted, except position 6 here has been changed from a 1 to a 0. So a single error. Now if this is a decent code, we should be able to correct this because there's only one error. So the syndrome we calculate by multiplying this received vector by H transpose. So we get this plus this plus this. And that's going to give us 1, 1, 1. We get 1, 0, 1 plus 1, 1, 0 is 0, 1, 0 plus 1, 0, 1 is 1, 1, 1. So this is our syndrome. And if we write out the syndrome equations, then we know that the the three parity check equations are that for error vector E, E0 plus E3 plus E5 plus E6 must equal 0. And E1 plus E3 plus E4 plus E5 must equal 0. And E2 plus E4 plus E5 plus E6 must equal 0. Those are the three parity check equations for this H matrix. Okay, and writing those out, excuse me, not equal 0. They must equal the syndrome bits, which we've calculated each of them to be 1. So each of these sums that I just read off must equal a 1. Okay, if this error pattern is consistent with the syndrome that we calculated from this received sequence. Okay, and we said there's going to be 2 to the k possibilities that are consistent with a set of equations. This is a 7-4 code, k is equal to 4, so that's 16 different possibilities. And these are the 16. And you can see kind of there's an obvious one. If E0, E1, and E2 are equal to 1, and E3 through E6 are all zeros, then these are satisfied. So E0, E1, and E2 equal to 1, and the others equal to 0. This is that solution. Is it easy to see what the other solutions are if you just started with this one? You're nodding. Can you tell me? So if I just start with this one, or can anybody tell me, I can say, all right, E0, E1, and E2 equal to 1. All of these equal to 0. That satisfies this. How would I generate the other 15 solutions?
E0 is E2, E2 is 0, only E4 is 1, E3, E5, E6, all 0.
Yeah, you could go through and just look, but is there a simple way of, once you've got one error pattern which satisfies the syndrome, of generating all the others? I mean, if you add a code word to that error pattern, that's going to give you the same syndrome, right? Because the code word times H transpose is equal to 0. So that won't change the syndrome. So we can just look at this thing and see that 3 1s here and everything else being 0 is a solution. And we can add the 16 code words to this vector, and that's these 16 error patterns. Those are going to be the error patterns consistent with this syndrome. And by the way, the all 0 code word is a code word, and that all 0 added to this is this one. And then the 15 non-zero code words give us the other 15 things on the list. Now what the maximum likelihood decoding rule said that we want to do with this is we want to find the error pattern in the list which has the lowest weight. These could all give this syndrome. What's the one in the list with the lowest weight? Well, here's one right here with weight only 1. Okay, the others look like they all have higher weights. Okay, so this is a unique lowest weight error pattern in this case. So this is going to be our most likely candidate. So if we add, and that was in fact, remember we said, so if we add the receive vector to this, which puts a 1 in here, we get back to our code word V, which was correct in this case because we assumed only one error. And this code is guaranteed to be able to correct any single error. So this is the most likely solution. Well, this is the end. Actually, this went much faster than the first lecture. Okay, so what you're going to hear about this afternoon, you're going to hear a little bit, I mean, this is, there's a method of decoding here called the standard array decoding and things like this. You'll hear about that this afternoon. You'll hear about how to design codes, generator matrices, so that the minimum distance is large. Clearly, if you have a code with minimum distance 3, so there's no two code words closer than distance 3, you'll always be able to correct a single error. Because if your only position, a single error would put you only distance 1 from the code word you sent. If the minimum distance was 3, you'd still be at least distance 2, maybe more, could be distance 4, from every other code word. So this minimum distance decoding rule will always decode correctly if there's a single error if your minimum distance is 3. If your minimum distance is 4, you're also going to guaranteed to correct a single error, and it's possible at some combinations that you'll be able to correct some patterns of double errors, 2 errors in a transmission, but maybe not all of them, because you could, if you have a code word of weight 2 and your 2 errors just happen to change 2 positions where these 2 code words differ, then you'd be the same distance from the other one. So you'd have to guess in that case. So you're not guaranteed to be correct. But you can kind of see from this argument that if the minimum distance is an odd number, you're always able to correct 1 less than half, or the integer part of half of that minimum distance. And if it's an even number, you can correct 1 less than half of the minimum distance. So you can start to get rules as to how to design good codes in terms of good minimum distance and good error correcting capability. Any questions on this?
Yeah. A parity code word other than the actual transforming code word, then an undetected error occurs. So how are we going to deal with these cases?
Well, nothing is perfect. You just have errors. I mean, the only way you could deal with this if you didn't want to allow a certain probability of having an error is to use extremely large codes. Okay, anytime you're talking about codes of finite length or short length, there's always going to be some probability of undetected error. And now there may be sometimes what you can do is you can have a second, like I say, this could be part of a network where you would have a higher layer, and you could have some kind of an additional overall check on your message. Otherwise, you can use something called a cyclic redundancy check as an example of this, and you can actually you take your message and you encode it first with this cyclic redundancy check, which just adds a very small number of parity bits. But then you take that and treat it as the message, and you have a second stage of encoding where you try to correct errors. And if you don't detect any errors on that second stage of decoding, you can still use the cyclic redundancy check to see if those equations are satisfied. And if they aren't, then you can toss out that message. If it's a system, if it's a two-way system, you could ask for retransmission. In internet type protocols use this kind of repeat request. I just referred to it briefly previously, that you could use to retransmit until you don't detect any errors. There's still some probability that was your next question. Yeah, that's because it's just another linear code. And there's still some probability, but you can pick that code to have an extremely small probability of undetected error compared to this. And it costs you only a little bit in terms of additional redundancy. So that's something you can. Pardon?
some additional scheme is needed to decode.
Yeah, if you want to, I mean, if you want to, okay, this is maybe a good discussion. If you want to avoid, really achieve extremely low undetected error probabilities with codes of reasonable length, like I say, you can always use extremely large codes, which get complex, and there you can, according to Shannon, if you design them properly, you can get extremely low error probabilities. But if you want to do them with finite length codes, it's oftentimes better to use the term for it is concatenation, concatenated codes. This is what we're talking about, is a form of concatenated codes, where you can use two codes in tandem. And the combined effect is that you get an undetected error probability, say in the example we're talking about here, that is much better than you could get with, you'd have to use an extremely long code to get that undetected error probability with a single code. But with two codes operating in tandem, you can get it more simply. So this concatenation idea is something that, I mean, turbo codes are a form of concatenation. There's lots of, there's various standards that have been based on concatenated codes over the years. The general idea is that you can use two codes of moderate length and therefore moderate complexity to get the same performance that you can with one much bigger code, which would be more complex. But with the advent of like low density parity check codes now becoming popular, there the complexity only grows linearly with block length. So you don't pay, a lot of the methods, the standard methods that people use with shorter codes that were used in the past, like, this little example is a Hamming code, BCH codes, Reed-Solomon codes, short constraint length convolutional codes and things like that. The decoding complexity grows more than linearly with block length. So you're kind of constrained by complexity to use shorter length codes. And the concatenation can be really advantageous then. If you have a coding scheme like low density parity check codes where the decoding complexity doesn't grows only linearly with block length, then there's less need for concatenation. Some of these problems about how to design codes that get close to capacity on certain channels, on noisy channels with reasonable complexity have been solved in recent years. The low density parity check codes, polar codes, turbo codes to a certain extent. But there's lots of systems level questions like this which depend on the application, which still make for a lot of interesting coding problems in terms of both research and industrial applications. Sure, that's a dual code actually. If you use, say you design a code with a parity check matrix, and then you decide to make that a generator, use that same matrix as a generator matrix, that becomes the dual code. The rate is flipped. So rate 3/4 would become rate 1/4. But the proper, and the minimum distance properties and everything are different too. But basically if a code is good, its dual code will also be good. Okay, it's not like you're going to form the dual code and come up with a really crummy code, because the properties are similar that you need in the parity check matrix and the generator matrix. So you can do that, and sometimes dual codes are of interest because they might make decoding a little easier. You can sometimes decode based on a dual code, and then you can, which maybe have a simpler structure, and then you can convert back at the end to get your actual code word. Okay, thank you for your attention.